I'm going to give you some tips for post-lab 9 voltaic cells. The first question on the post-lab pertains to part 1 of the experiment. In this part of the experiment, you mixed these 3 metals with these 3 solutions in 6 different combinations. You did not mix the copper with copper or the iron with iron or zinc with zinc, so I'm just going to cross those off. In each box, you're going to record whether or not you observed a reaction between the corresponding substances. If no reaction was observed, then you'll just write no reaction and R in the box. And again, I don't know if this is correct or not. I'm just doing that as an example. If you do observe a reaction, you are going to write a balanced net ionic equation in the box to describe that reaction. And here's an example of a balanced net ionic equation. So if you did observe a reaction between zinc and copper 2 nitrate, you would just simply write the balanced net ionic equation in this box. Now, one thing that can be a little bit tricky is recognizing the respective cations in each one of these metal solutions. The copper 2 nitrate solution is reacting as the copper 2 plus ion. The iron 2 sulfate solution is reacting as the iron 2 plus ion, and the zinc nitrate solution is reacting as the zinc 2 plus ion. So if you did observe a reaction between the zinc and the copper 2 plus, you would just simply write a reaction between solid zinc and copper 2 plus ions. Those are going to be aqueous. Actually, you can leave the states off so that it fits in the box. And then you would just need to predict the products of this reaction. I'll let you figure that part out yourself. For part number 2, you created 2 voltaic cells, and in this, so the first cell that you created was between copper and zinc, and in this box you will be reporting the voltage that you recorded after you made that cell and you measured its voltage. And then in this box here, you're going to write the balanced net ionic equation for the actual reaction that was taking place in the cell. So you know that the reaction was occurring with copper and zinc. One of the possible half reactions is the copper going to copper 2 plus and 2 electrons, and the other possible half reaction is the zinc going to the zinc 2 plus ion and 2 electrons. Both of these are written as oxidation reactions, but only one of them is actually an oxidation reaction and the other one is a reduction reaction in your cell. So your challenge is to figure out with these 2 half reactions which one is the oxidation and which one is the reduction. You're going to do that by looking up the half reactions, looking up the voltage for each of these half reactions in a data table. So you'll just consult a normal data table of reduction reactions, and you'll look up the voltages for each of those, and then you're going to remember that your voltage that you measured, that's your E cell, and E cell comes from the cathode minus the anode. So what you're going to do is test out the 2 possible options for fitting these numbers into the E cell equation. You'll try this as the cathode and try this as the anode and see if that gives you the correct E cell. If it doesn't, try it the other way around. Try this one as your anode, try this one as your cathode, see if it gives you the correct voltage. That's going to be the way that you determine which of these is the cathode and which of these is the anode. And once you have figured that out, then you're going to use the trick red cat to help you remember that the reduction is taking place at the cathode. So let's say that we decided this is the reaction occurring at the cathode. We therefore know that this is actually a reduction reaction and we need to write it as a reduction reaction. Once you get the equations in the correct order, then you're just going to combine them to give you the overall equation. So this one is a little bit tricky. Then the last problem on here, you made a 3rd voltaic cell. At this time, the cell was made from copper and an unknown substance, so you don't know what it is. You measured the voltage of that cell and you reported it right here. Now, you know that one of the components of the cell is the copper 2 plus, and you'll be looking the voltage up of that half reaction and write it down here. Then you're going to report the reduction potential of your unknown. Now, to do that, again, you're going to use that same reaction, E cell is cathode minus anode. And you know the value of E cell because you reported it in the lab, and you know the value of one or the other, either the cathode or the anode, but you don't have any way of knowing at this time whether the copper is the cathode or the anode. So you're going to plug in your value of E cell, and let's just say plug in copper as the cathode and come up with a potential value for the anode, and then just make a note of that over on the side. I'm just going to write it as E, not as a cathode or as an anode. And then you'll try it in the other option. So you'll plug in your voltage as E cell. You'll plug in your copper as, like, let's pretend like maybe it's the anode this time, and calculate a voltage for if the unknown is actually the cathode. So you're going to begin by getting two different voltage values for the unknown metal. And again, this is because we originally don't know if copper is the cathode or if copper is the anode. So we've got to consider both options. Then you're going to go back to that same table of reduction potentials, and you're going to find a substance that has either this or this reduction potential. The possible identities of your metal are one of these 6 substances. Don't expect your value to be exactly the same as one of these 6 substances, but it should be pretty close. You're going to find the thing that it makes the most sense. Once you have figured out what the actual substance is, you are going to cross off the voltage that is not actually correct, use just the correct voltage, and then also report the identity of your unknown metal, whatever it might be. I underlined magnesium, but I don't know if that's what it's going to be.